The theory of constraints is a process improvement methodology that emphasizes the importance of identifying the system constraint or bottleneck. By leveraging this constraint, organizations can achieve their financial goals while delivering on time in full to customers, avoiding stockouts in the supply chain, reducing lead time, etc. With this simple value stream, to produce products A and B, we want to illustrate the way to maximize profit taking into account the system constraints. Each product is made by assembling two subassemblies, one of them common to both products. The process consists of three sequential operations for which there are special purpose workstations with a corresponding operator each trained for the specific job. Manufacturing, test, assembly. The line operates one shift with 2,400 productive minutes per week. The fixed costs, which include the salaries of the three operators, are €8,000 per week. Sales price for the finished products: A. €90. B. €100. The maximum weekly market demand is A. 200. B. 100. Total materials cost: A. €50. B. €40. We want to know how many products A and how many B we should produce to maximize profit. We want to maximize overall profit, so we calculate the margin of each product by subtracting price minus materials cost. Since we can't satisfy all the market demand, we must decide which product should be our priority. If we ask finance, they will tell us B is the best, since it has the highest margin. Let's see how many resources we will need to produce all the market demand for B, and how many A's we will be able to produce with the remaining resources. With the remaining capacity for product A, we can manufacture 140. Only test 40. Assemble 380. It makes no sense to manufacture more A's than we can test. The excess assembly capacity will be wasted, because we can only assemble the units which have been tested. This means that in fact we will only be able to produce 100 B's and 40 A's. This gives us a total loss per week of €400. Maybe the finance criteria of giving priority to the product with the highest margin was not so good after all. We have already noticed that the bottleneck in this line is test. It is limiting the effective capacity of the whole line. The use of bottleneck time is, therefore, a critical factor we should consider to optimize the line. We need to ask ourselves, how much bottleneck time is consumed to obtain a €40 margin in product A, and the same for product B. This means that each minute of test time, bottleneck, if used to test product A gives us a margin of €4 while product B only gives us €3. Product A is, therefore, more profitable in these circumstances. So, when we take into consideration the existing constraints, A is more profitable. Let's give priority to A, and use the remaining capacity to produce B. It is, indeed, more profitable to maximize product A in this case, in spite of its lower margin. The bottleneck plays an important role in finding the optimal solution. It defines the effective capacity of the whole line, therefore we need to optimize the use of bottleneck time. Let's now look at the problem graphically. The red area is the forbidden area, due to the constraints, maximum A, maximum B, and the constraint of the 2,400 minutes available at the bottleneck test. Each A consumes 10 minutes of test and each B 20 minutes. We now look at the point of maximum profit. It will be the furthest point from the origin, within the allowed area, green, which is the point of maximum A, 200 units, and 20 units of B. Download this Excel file solver1.xlsx from OneDrive. Open Sheet Production. Now let's see how to solve the problem with Microsoft Excel Solver. First we need to set all the data in a spreadsheet. In matrix B3D4, we have the unit times for each operation in products A and B. Column E has material costs and F product selling price. In column G, margin, we need a formula which just subtracts F minus E. In column H, produced, we want Solver to place the results we are looking for, number of products A and B to produce. Column I has the market constraints for A and B. Row 5 has the formulas above to calculate time consumed on each operation based on the products produced. These values we will compare with row 6, available times for each operation. Finally, B10 has the shown formula to calculate the profit. This is the cell we will ask Solver to maximize. Now we go to Solver to set up the parameters as shown. We want to maximize profit, cell B10, changing cells H3 H4 where Solver will place the solution we are looking for. The constraints in Solver. B5 D5 less than or equal to B6 D6 use times less than or equal to available times. H3 H4 less than or equal to I3 I4 don't produce above market demand. H3 H4 must be integers and not negative. Press resolve and we will get the results. We come to the results we obtained before. Now imagine that an engineer has found a way to reduce test time of product A from a total of 10 minutes to 9 minutes by adding some work to the assembly operation, which would involve an increase from the previous time of 5 minutes to 7. This suggestion would be difficult to justify with finance, since we are increasing the overall operator time of product A 1 minute. But let us look at our Excel to see what Solver has to say. We have been able to produce 10 more Bs, increasing the profit from €1,200 to €1,800. This is telling us that, maybe, the way we compute product profit may not help when we have idle time in some of the operations. Open sheet distribution in our Solver 1 file. Now let's see another example of theory of constraint solution with Solver. In this case we want to minimize the cost of distribution of goods containers from warehouses X, Y, Z to shops A to F. Matrix C4H6 contains the transport costs of one container from each warehouse to each shop. Matrix C9H11 will contain the number of containers from each warehouse to each shop we are looking for. The blue cells have the formulas shown. We want to minimize cell C15. Notice we must meet all the shop's requirements, C12H12 equals C13H13. This is the optimal solution which meets all the constraints. OR notes are a series of introductory notes on topics that fall under the broad heading of the field of operations research, OR. They were originally used by J. E. Beasley in an introductory or course at Imperial College. We will solve this problem with Excel Solver. The data is in sheet cargo. You can check the formulas already in the blue cells. Constraints are available cargoes, compartment capacities, maximum compartment loads, compartment load balancing. We run Solver to get the optimal solution which meets all constraints. These are some conclusions. All value streams are subject to multiple constraints such as time, cost, delivery, workforce, market demand. The optimal operating point very much depends on the existing system constraints which may vary a long time. Product cost and profit depend on capacity utilization. Microsoft Excel Solver is useful to optimize a value stream which is subject to multiple constraints. See in Polyhedrica blogspot. We can clearly see that, due to the existing constraints, this line is very inefficient. Let's look at the capacity utilization of each operation. The only operation with 100% utilization is test. This is what we would expect, since it is the bottleneck. We see that final assembly has very low utilization, less than 50%. We can see that the only way to improve further the productivity is to reduce test time by making it more efficient, or to transfer some work, if possible, to the assembly operation.